Hi, my name is Isak van der Westeren. I've decided to do a very interesting exercise. We are going to scale the universe down so that the orbit of the Earth is the size of, say, a 50-cent coin. So let's assume that coin has a diameter of, say, 2 centimeters, and the radius of that coin is 1 centimeter, and that is 1 astronomical unit, or the distance between the sun that is in the center of the coin to the edge of the coin where the orbit of the Earth will be. And so we're going to scale the universe down and the solar system, everything, and look at some important distances and diameters. So I've done it in a file, and I'm going to load the file. We're not going to waste too much time on this. The file's name is coinau.txt. We open the file. Let's take out the file, and we can hit evaluate, because the parser is good with units, and I've also enabled monitoring, so all the values is already here. So let's just quickly drop down the report. There you will see the solution, but let's start with the source. That is the evaluate source expressions. Those are the expressions in this line here, but it's nicely listed under each other so that you can easily see what I've actually entered. This is a valid source expressions. Look at the upper part, and then we're going to do the lower part. I'm not going to explain it all. It's all on the screen. You can see it all there. So that is all the source expressions. We can't go lower. So you can pause and study these. So pause and study, and we go down, pause and study the last bit. And that is the solution, and you can pause and study. But let's not waste too much time on this, because it's all in the monitor list box here, the results. But if you want to know how I calculate, I just googled every distance and thing, and I scale it down. So let's look at a few. I've calculated a scalar. I first defined the AU, or the distance between the Earth and the Sun. That is a 1 centimeter radius of a coin, and so the actual AU is a number of kilometers, so I've said scalar is equal to 1 centimeter over an AU, and that gives us a scale factor of 6.68458 wara times 10 to the power of minus 14. So it's a massive scale down. That is a very small number. Okay, so now a speed of light is an interesting figure we would love to know. So what will the speed of light be if we scale it down with that scalar? So the speed of light will become the scalar times c, that is just the speed of light, like E is equal to mc squared. That is c of that formula. That c stands for the speed of light. So a speed of light will be very slow now, the syrupy speed of only 1.202 whatever millimeters per minute. So it's just over 1 1/5 of a millimeter per minute. So the speed of light will be extremely slow with that massive scale down factor. So you understand, we are talking about this orbit of the sun, the size of a coin. So that will be then the speed of light. So this is a scale down values as we get as answers here. Now 1 light year, if we scale it down, will be scalar times a light year, and that will be a distance of 632.397 meter. That's quite massive compared to a 2 centimeter diameter coin that is the orbit of the Earth with the sun in the middle. Now the Earth to the moon distance will only be, that is a real distance, times the scalar, of course, there, and it will be only 25.69 whatever you can see the precision there, micrometers. Now that is not milli, that's a thousand of a millimeter, the micrometer. So that is only 25 millionth of a meter, or 25.69 thousandths of a millimeter. The radius of the sun is actually bigger than the Earth to Moon. That is a radius from the center of the sun to its surface. It's actually bigger. As you see, the Earth, if you take the Earth as a center, the Moon around it, that is kind of a radius, is 25.69 micrometer, but the sun center to its surface is 46.547 micrometer. So it's nearly double as much, nearly 50, So the sun is quite big. It's actually nearly double as big if you take it from the Earth at its center and the Moon. That distance from the Earth to the Moon, the radius of the sun is much more. It's nearly double that distance from the Earth to the Moon, the radius of the sun. So the sun center to its surface is much further than the Earth to the Moon, and that's interesting. And you only realize it if you could do the comparison actually. Now, the closest planet to the sun is Mercury. So we're going to see how many millimeters will that be if the Earth is on the outer edge of a 2 centimeter coil with the sun in the middle. Mercury to the sun, the closest planet, will be 3.877. Remember, the values I get from Google is not very exact. So by that will be about 3.8 millimeters. Okay, so that is much smaller than a centimeter. So it's 0.3877 centimeter. If we take the Earth from the sun, is 1 centimeter. Now Venus to sun, a scalar times 108 gigameter, and that is 7.219 millimeters. Okay, diameter of the Earth is scalar times 12,742 kilometer, or 12.742 megameter, and that is only 851.75, not micrometers, nanometers. Now that is 10 to the power of -9 meter, né? So this Earth is like a small thing. It's like a germ, maybe a virus, compared to the coin. So the Earth is very small now in the sky. So it's only like nanometers. 850 is less than a micrometer. Now the Earth to the sun is scalar times, of course, the astronomical unit is a distance to the Earth, and because we scale it to 1 centimeter, it is exactly 1 centimeter. Now Mars, that's Earth to Sun, Sun-Earth distance is 1 centimeter in the sky. So that's 1 centimeter correct. Mars to the Sun, and that's the next planet out from the Earth. That is scalar times 228 gigameters. And that is 1.5, 1.5 centimeter basically. 1.5 to 4 centimeter. Now Jupiter is the next planet after Mars to Sun. Is Jupiter is 778 gigameters or million kilometers from the Sun, and that is 5.2 astronomical units, or 5.2 centimeter. We remember astronomical unit is now a centimeter. So Saturn to Sun will be scalar times 886 million miles, or that mega mile. You can use our unit prefixes on old units or in the library. So 886 million miles is will amount to 9.5314 astronomical units or centimeter. Remember, the astronomical unit is the distance between the sun and the earth, and on our coin it is 1 centimeter. So Saturn is about 9.5 centimeters out from the center of the coin. Uranus to the sun is scalar times 19.8 astronomical units, and that is 19.8 centimeters from the center of the coin. We're going to get big distances now later on. Neptune to Sun scalar times 30 astronomical units, that's 30 centimeters. Now we're on the outer edges of the outer planet. That's the outermost planet. Pluto is not really. It's not that. It's a dwarf planet, but Neptune is a large planet, a real planet out, or normal planet. Pluto to Sun. Now, remember, some of these planets, like Mercury and Pluto, have very eccentric orbits, but so we are working with average values. So this is 39 centimeters, quite big. Now, this from the center of the coil, we're nearly at 40 centimeters. Now, obviously, you get the Oort cloud. Further out, né? So you can still, the solar system is quite big, but a light year we know, say the solar system it's about 632 meters. You see, so a light year is quite a big distance. If its Pluto is only 39 centimeters from the center of the coin, but now we're going to go to the stars. Now we know stars are also like the sun. I'm talking about main sequence stars. I'm not talking about black holes and strange stars, but I think the sun is yellow dwarf, they would call it. Oh yeah. So Proxima Centauri, I think, uh, is quite a cool star. It's a red dwarf, I think. It's the closest star to us. That's why it's called Proxima Centauri. It's the closest star. It's near Alpha Centauri. Now, Proxima Centauri to the Sun, if you scale it down, that is 4.25 light years. That's the closest star. Will be 2.687 kilometers from our sun in the center of the coin. And we are on the earth is on the outside of the coin of 2 centimeters. So one astronomical unit is 1 centimeter. That's the distance between the sun and the earth. And the closest star is already 2.68 on this very much reduced universe of us, kilometers out from the center of that coin. So, and we can see the star as the closest star, and it's actually quite far. So we're working with kilometers and hundreds of and tens of kilometers when we're looking at stars. Alpha Centauri, the next pair of stars out is Alpha Centauri A and B. Those are stars. They are sun-like. Stars are similar to the sun, but they are probably also red stars. I'm not sure. You must read up. I've just used these numbers that I googled. Now that's scalar 0.4. Now Proxima Centauri is 4.25 light years, and Google give Alpha Centauri, the pair of stars A and B, it's probably a binary pair, is 4.35 light years. Now that is now, instead of 2.68, now 2.75 kilometers out from the center of the coin. The sun is in the middle. And the sun, is a micrometer small. It's 46 micrometers, the radius of the sun. Now the Milky Way, compared to this coin, if you scale it down, will be 33.422 megameters. Now, megameter is basically 1,000 kilometer. So 33,422,000 kilometers is a radius of the Milky Way. And we are 16,000 kilometers, 16,442.328, whatever, thousand kilometers from the galactic center of the Milky Way. Now that galactic center is Sagittarius A star, and it is a supermassive black hole. Okay, now that is a distance between us and the supermassive black hole that keeps the Milky Way galaxy basically together with what we call dark matter. Okay, then that's our distance to the galactic center. If we scale it down to a coin, is 16.44 megameters or 1,000 kilometers. And we can actually see that center. It's amazing. Now, the radius is bigger. That is 16,000, and that is 33,000 kilometers. Okay, that's megameters, 1,000 kilometers. If the universe is as big as a coin, but now things become very interesting. Our Milky Way has a large, big galaxy outside it that is on its way. It's going to collide with us in around, say, 4 billion years. That thing is about 2.5 million light years from us. Okay, and that thing in this scale, if we scale it down 2.5 million light years scale down with the scalar, we get a distance of 1.58099 gigameters. That is like million kilometers, I think. Like a megameter, 1,000 kilometers. Now, that is just from the center of a coin, eh? So we are looking, and we can see this Andromeda. It is 2.5 million kilometers from the center of the scale down universe on a coin, and that is the actual scale down distance now. So that is how far 2.5 million light years is. If you scale down the distance between the Earth and the Sun to 1 centimeter, it will still be 1.5 million gigameters. Mega is million, but giga is billion. Now, billion meters is million kilometers. So 1.5 million kilometers will be Andromeda galaxy. And we are sitting here in the Milky Way, probably the center of the distance between the black holes at the centers of the galaxies. That supermassive black. That's probably the distance there. So I'm not sure how they measure it, but it's probably from center to center. So 1.5 million kilometers. If the Earth is orbiters, the Earth is the size of a coin. Now, the observable universe radius, I also only call it observable radius because that is how far you can basically see. The observable universe radius. Now, it takes obviously the expansion of the universe into account because we're looking back in time here. So probably you don't really look at full distance because the further you look, the closer it will be than it actually is. But let's say they say the observable universe has a diameter of 46.508 billion light years. Now, a billion is a giga. Now, 46.5 giga light years uh, times scalar. Well, if our Earth orbit is the size of a coin, will be 29.41 terameters. Now you can do the conversion. That is million kilometer, ne? Giga, a million is mega actually, but gigameters, million kilometer. So we're talking about a radius of 29.5 gigatera, ne? 29.4 billion kilometers. If the Earth's orbit is the size of a coin. Imagine that, 29.4 billion kilometers. If the orbit of the Earth is the size of a coin. So I think you've got it now. So there you can study it, and there's a source. So you can freeze the study here. I'm going to give you another chance, and then that's the upper part of the source, and that's the lower part of the source, and there we have our upper. I'm going to kill the sorter. There's all your variables, and I've put monitor on you. I checked all these boxes, so monitors all the variables, and that is just the plain values without showing the calculation. So this is the upper part of the monitor values up to Proxima Centauri, and then we're going to drop it down, and you can pause and study that also. And it's very interesting to see how huge the universe actually is. And it gives you a very good idea. You understand micro and million meters and your unit gets a very, very accurate relativity of the universe. And it's extremely large. So it's all here. That's a lower part. Can't go down further. So you can pause. So you pause that part and you study it, and then you pause that part and you just study the rest. And that's all I have to say. So obviously it's not all the distances and sizes in the solar system, but those are the main ones, and gives you a very good idea what's going on. So I'm not going to make this video too long. It's all on the screen. It's all there. So let's go up there, pause a study the rest. That is what you want. And then ponder about these numbers, and these look at the units, micro, nano, milli, centi, milli, kilo, mega, giga, tera, and understand what it means. And if you want to know what it means, I'm going to drop down the library for you, and there your unit prefixes is defined in the upper part. Okay, there you all have it, what it actually means. So look there. There's all your multipliers. That's all your big numbers. There's giga, G. That's there's the prefix itself, its name and its value. So and then the one that makes it smaller, like centi, deci, centi, milli, micro, nano, pico. You don't all have to go to these fem2 and we're it's probably on the multipliers we stop at, I think, tera or giga, and on the sub multiplier I think we stop at nano. But if you want to learn them, this is a good place somewhere now to learn them, So this is all your unit. This is the upper part of your library. And obviously, the library just defined a lot of predefined names and their values, like yard, that. And I'm not going to go to some older units. There's actually many units, most units are here. But some of them don't work due to name clashes, but there's a lot of information here. And you can enable the library or disable the library. I think so. One of these, let's say, micro. Where do we enable? Let's look at some. I think it's the upper one. No, it's not that. That's your report. I think it's a setting that you can enable and disable your library. That's why. Yeah. So I'm going to stop it. I don't know, but you can. Okay, maybe somewhere else. Library on, library off. You can definitely switch the library on and off. Oh yeah, natuurlijk, there it is. I don't know why I didn't see that. Check is library on, uncheck. Let me just get that thing. You can see it at the bottom if I'm there, So check. Look at the bottom left on the bar. Check is library on and uncheck is library off. So the library is active now. So that's why it understands some of the units like miles and things. Okay, let's stop the video. This is me. That is my younger self. I've written this program. There's some things that I would like to improve, maybe still before I would like to give it to people, but it's already okay. It's quite a good program, you see. You don't have to worry about unit conversions. You see, that's a beauty of it, and it makes it so much easier. So it's a very nice calculation system. I think it can be a world standard. It's use type SE values, and that's a whole series of videos all about. And this is a nice demonstration of the niceness of having units built into your values. And that's the whole thing. What type SE values? You type SE values also is not simplex. It's complex with units. Plus, you can do first and second order differentiation because the type SE value, the number part of it, type SE number, has actually three radiuses. That you multiply with a unit vector with a complex angle, and then the unit. That radius part has three radiuses, and every time you do a calculation, the calculation is done on every one of those radiuses independently. So the top numbers, if you say multiply number A with number B, then the top number of number A is multiplied with the top number of number B. And the bottom mid number of value A is multiplied with a mid number of value B if you multiply, and so the bottom number is also multiplied of A with the bottom number of B. That means if you inject a split, a dx say split, and you do some operation or function on it, then you will get three answers basically internally, and those answers will not have the same split like dx originally after the calculation. So before the calculation, the split is a dx that you inject to inject the splitting or a difference between the three values, and the mid number is like the average or the middle number, and you have 3 points on the graph. So that dx is then injected, and the three numbers migrate apart by a distance of dx. Okay, that's what you inject. That's how you do differentiation. Unfortunately, the videos in Afrikaans, but that's basically what happened internally. And when you do your calculations, every channel is independently going through that calculation. The top channel, the mid channel, and the bottom channel. That's because you have three channels and they're like stereo, no? So, but it's like three channel stereo because we want up to second order differentiation. So now to get your first differential, you simply divide your final difference over your original difference. So this di over dx. So di is your final difference between these three values, and dx is your initial value before the calculation that you injected. So you inject the dx, you do your calculation in stereo on three independently, the top, the independent, the bottom, the middle, the independent, the top. Now you get your final three answers, but I don't look for differentiation exactly to the answers. We don't want a value, we want the differential. So I look at the differences between the values, and I get two differences between the top and the mid num. I get the difference, and between the mid and the bottom num, I get a difference, and I take the average of the two difference, and that's dy. And if you divide dy over the initial dx, di is the average of 2, then you get your first differential. Now, the second differential, I can't really explain now. It's a bit complicated, but basically comes down to if you have your first differential as a graph, and you have, then you need two differences now, to get the differential of the first differential. So the dy is a second split or the second differential, and that one is actually equivalent to d squared y, and then you divide it by the initial dx to the power of 2, and then you get your second order differential. And there is a video about it, so you should understand that. Okay, I'm going to stop this video. It's becoming too long now. Okay, my friends, I hope you enjoyed it. Parcel is not without any value. I think people should take this serious. There's a few things that I might like to change. One thing I would like to have is maybe uh, have an answer in terms of a variable, not only units. Um, I don't know if the way the parser works make it possible to have your answer in terms of a unit. Say I say AU is so many kilometers, and I want something in terms of AU. So I think AU is also built into the library, but somehow I think it's in lowercase letters AU, and U can stand for what? U is actually some unit, and I is atu. So atu U. I don't know why, but doesn't give the right value. So I had to specify AU as a variable. Now variable kind of get precedence over a library unit. But you should not use internal units as variables. Yeah, so it's quite an issue of name clashings that you can get, and so there's still a bit of work to reduce name clashing. But I've done quite a lot of work already on that. But maybe I must just simplify my library a bit. But if you have a library unit that clashes with the internal unit, even if it's got prescaler. It cannot libraries should not clash with internal units. Internal units always get precedence, but variables also get precedence over library units. Okay, because if you specify something in a variable, you want to use that, so that should get precedence. Okay, my friends, I hope you enjoyed it. Bye bye. I'm going to stop the video now. It's found that button. And have a lovely day, and hope you enjoyed this. Bye.